In this video, I'm going to talk about Hodge filtration, Hodge cycle, and Hodge conjecture. If you already know what is Hodge conjecture, you might enjoy this video because it is slightly different from whatever exists in the literature. So, as usual, we start with a projective variety that is smooth projective variety over a field K, characteristic K equal to 0. So in the first video, we introduced the algebraic de Rham cohomology. And in this video, we show that this algebraic de Rham cohomology, x over k, has a natural filtration. And what is this filtration? Its pieces, fk, it is given by image of, its image is given by the image of the hypercohomology of this truncated complex inside the hypercohomology of the full complex of differential. So what is this truncated complex? So starting from omega k, it is just the usual differential forms. So omega k plus 1 until omega n. But the differential forms, k minus 1, 0 form, 1 form, and k minus 1 form, we just put 0. And this is still a complex because at the end, dd is equal to 0. And the point is that this is a subcomplex of the usual complex of differential. So I have written already the usual complex of differential forms on x. So you see that on top of omega 0 until omega k minus 1, we have, I just put 0. And after omega k, I write the full set of differential form. So we have this inclusion from here to here. These are identity maps, and this is just 0 inside the set of differential form. So we have denoted this one by a bullet bigger than equal to k, x, k, and this is the other one is just the omega bullet x over k. And what it is easy to see that when we have a morphism of complexes, we will have a map from their hypercohomology too. So we have the map from the hypercohomology of this one, x, to here. And so fk is just the image of this map. So let's go to a more computational way of seeing the Hodge filtration. So I forgot, this is called Hodge filtration. Okay, so recall the double complex that we used in order to define the hypercohomology, this SIG notation. And remember that the n element of the hypercohomology we denoted by omega in HM de Rham algebraic. It was just omega 0 plus omega 1 plus omega m. Omega 0 was a bunch of 0 forms, omega 1 bunch of 1 forms until omega, so we have omega k minus 1, omega k, and then it was going omega m. And remember that this way of writing, it is writing in the double complex of SIG that I had. Remember that going up was delta, going to the right was the usual differential of differential form. So an element, if this element is in f k, by the way, for simplicity, we sometimes just write fk here, and we don't write the cohomology itself. So if you have element here, then what this means that we don't have 0 form, we don't have 1 form, we don't have chi minus 1 form. So this means that this element will be until omega chi minus 1 will be 0. So at the end of the day, an element of fk of the hypercohomology is given by 0, 0, 0, and then start omega k, omega m. Two pieces of the Hodge filtration, it is easy to analyze. One is F0. So F0, we just, this guy becomes the full complex. It is just the whole de Rham cohomology. And the other one, which is also easy to analyze, is Fm. So what is Fm? Fm will turn out to be global closed, well, of course, algebraic M forms. And the reason is easy because if we look at in the double complex, so elements of Fm are just 0, and then there is just omega m here. So its delta must go to 0 because there is no contribution from this direction, and its d equal to 0. What this means, so remember that omega m was collection of differential n forms in open sets ui, omega m. So remember that omega m was a collection of differential n form defined in the chart open set ui. So delta of it equal to 0. This means that the omega m's, they glue to each other, they give a global differential form, and it's t equal to 0, so it is an exact form. Okay, so let us consider now a subvariety of x. This subvariety will be of dimension m half. So from now on, I am assuming that m is even. And also, from now on, I will work over the field of complex numbers. Well, if z is smooth, then the algebraic topology gives us a way to define this H element, the homology class of Z, inside the M's homology of Z. Remember that Z is of complex dimension M half, and so it is of real dimension M. So its homology class will be in HM. But smoothness here is not a problem. Actually, if Z is a singular, by the way, I have to remember that, let's for simplicity take this one irreducible. Of course, everything over C. If C is singular, then we will have desingularization of Z, and then this Z is inside X. And we will define this Z image of so Z tilde itself, there is a homology class of Z tilde inside HM Z tilde Z. So remember that this is now at the top cohomology of Z tilde, and there is no more cohomology for Z tilde on above this one. And so this will be the image of this guy under let's say HM Z tilde Z to HM X Z, which is obtained by this map here. Okay, let us recall also that our algebraic de Rham cohomology, the usual de Rham cohomology was isomorphic to algebraic de Rham cohomology of X. We call this map A, and its inverse A minus 1. So I will take omega in Fm plus 1. So this piece of the Hodge filtration is very important for us, because using this one, we will define the notion of Hodge cycles. So we take this an element here, and we can talk about the integration of omega over this homological class. remember that this integration, it means that we take this omega by this a minus 1 map, we go to this infinity cohomology, and then we, from algebraic topology, we know that this integration is well defined. It turns out that for any kind of integration, for you first you have to restrict your differential form to your topological cycle, and this I and a minus 1 map are compatible with the restriction, and this is going to be 0. And why this is the case? This is the case because by definition omega, it will be of the form omega m plus omega m minus 1 plus blah 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 until omega m half plus 1. So in particular, there is no differential for omega m blah 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 omega 0. So this differential form doesn't exist in the expression of omega. And when we restrict all these omega m minus 1, omega m half plus 1, this is identically 0. So the integration of 0 of any cycle, it is 0. So what we have used here, the fact this is the beta, there is no differential K-form over holomorphic differential form, holomorphic or algebraic K-form over a complex manifold of dimension K. And this is the reason is very easy, because if you take a holomorphic coordinate z1 until zk, and at the end if you take the differential forms are given by dz1 and dzk, and if you take k plus 1 of this one, there will be repetition, and this repetition will make that such a differential form is identically 0. Okay. So I assume that my algebraic cycle Z is irreducible, but actually this is not necessary. We can take algebraic cycle Ni, Zi, and let's say from I equal to S, and I's are integers, and Zi's are as above. And it turns out that for this one also we can define the homological class. This is just Ni, Zi. This is in HMXZ, and again what we have shown is, let's write here, that the integration of Fm half plus 1 over this guy by linearity, this is 0. Okay, so finally we reach to the definition of Hodge cycle. So delta in the homological class M X Z is called Hodge. If what happens? If when we integrate our delta, all the elements of this piece of the Hodge filtration, this piece of the Hodge filtration, then we will have 0. And from where it comes, this one, because we have proved that algebraic cycles, which by definition is just this Z and Zi, let's just take homologic class, are Hodge cycles. And here comes our protagonist, the Hodge conjecture. Hodge conjecture. So the first version of the Hodge conjecture is in this way: for any Hodge cycle, delta in the homology hm x z, there is, let's say, ni in z algebraic subvariety zi inside x, well, let's say I equal to 1, 2 until s, such that a delta is just a, sorry, without a for the moment, is just ni zi. This is actually called the integral Hodge conjecture. And right at the beginning of the invention of Hodge conjecture, Hertzsprung and Atiyah, they found counterexamples for this. So the reformulation was our rational number that if we want, I want to write with integers, it is like something like this. So there are ni's and algebraic cycles, and a in some another integer, non-zero integer, such that whenever I multiply a delta with a, then this will be my algebraic cycle. So any Hodge cycle, a multiply of it must be an algebraic cycle, and this conjecture is still open. So as I said, the reformulation of this conjecture with just a equal to 1, it is called integral Hodge conjecture. In general, it is wrong, but to understand in which cases it is true or it is false still is a great challenge. So, why the Hodge conjecture is so difficult? The main reason is that there is no method in algebraic geometry to construct algebraic cycles. And I want to show 3 statements from Pierre Delaine regarding this one. So here you see statements from Pierre Delaine, who is complaining about the lack of our knowledge about in constructing algebraic cycles. And as you see, it has to do with the motives and so on that we are not going to discuss in this talk. So what are the main evidences for the Hodge conjecture? The first main evidence is from where it comes. So it was delta algebraic implies that delta is Hodge. So whenever we have a P then Q statement in mathematics, we would like to understand if the Q then P is also true. And this is the main reason for the existence of the Hodge conjecture. Okay, but for which class of varieties we know, maybe the most famous one is the case 2n minus 2. In this case, we are dealing the i's are divisors, and we are talking about let's say the corresponding theorem is called the Lefschetz 1-1 theorem. And then the another case with m equal to 2, which this follows from the previous one, Lefschetz 1-1 theorem plus Hard-Lefschetz theorem. Once again, I want to emphasize that the main difficulty behind the Hodge conjecture is the lack of methods to construct algebraic cycles. Even in the case where the Hodge conjecture is true, explicit or effective construction of algebraic cycles are extremely difficult. And the main example for this one is the Fermat variety of degree 12. So if we take this one, this homogeneous polynomial degree 12, we project-wise, we will get a surface in P3, which is called the Fermat surface. And it is possible to write down a basis of Hodge cycles in this case, but there is no method to construct all curves in this variety which generate the space of Hodge cycles. So for this example, after a good amount of computation, we can prove that the rank of the Z module of Hodge cycle is actually 6, 4, 4, but the rank of the submodule of these generated by lines P1 inside X, it is 3, 2, 2. So I have to mention that the Fermat surface has a lot of lines. For example, if you just write x12 plus y12 plus z12 plus w12 in this format, x minus zeta12, zeta12 is the 12th root of a unity, then y blah blah blah. Actually here it must be 24th root of unity, so we can decompose this one, x minus zeta 24y plus zeta minus zeta 24w, some another polynomial, and so the line p1 given by x minus zeta 24y equal to z minus zeta 24w equal to 0, this line is inside the Fermat surface. And of course, we can do with the permutation of the variable and taking more roots of unity. So at the end, the rank generated by all these lines inside the lattice of Hodge cycle is 3, 2, 2. So this means that we have to still construct more cycles in order to verify the Hodge conjecture form at the Fermat surface. And actually, one of the person who tried to do this one, they called Aoki Shioda. They introduced more curves in order to reach 644, but they even, in this case, they realized that even they need more curves. So far, there is no complete list of algebraic curves generating the lattice of Hodge cycles, which in the case of surfaces, it's called also Picard group or Neren-Severi group. This part of the lecture is actually gathered in chapter 15 of my own book, which is written before my book with Roberto.